My name is Durga Prasad. The topic today is about failure sense, detecting sensor failure using electrical appliances in the home. The paper is published in 2014 IEEE 11th International Conference. The link is provided in the description. The authors are Sriraja Munir and John A. Stankovich. This paper was supported in part of NSF grants and a gift from Park Palo Alto. The following is agenda for whole presentation. It includes introduction, related work, approach, evaluation, discussion, and finally, a conclusion. Ever asked Google Home or Alexa to turn on a light for you? And did it turn it on? If it did, then that's fine, but what if it did not? Also, what about that motion sensor which will turn on the light even though no one is around? Have you tried to debug why the sensor is acting strange? Well, to solve these and many other issues, failure sense comes into play. So, what is failure sense? It is a solution to detect sensor failure at home using electrical appliances such as lights, fans, televisions, and all other electronic equipment which use sensors to turn on or off. Failure sense also detects not only fail-stop failure, but obstructed view and move location failures that are very difficult to detect even if sensors are made highly reliable and are not addressed well enough to date. Fail-stop failure happens when a sensor fails and stops reporting. It may happen due to a hardware failure or power outage. Obstructed view failure happens when a sensor's field of view is compromised. A motion sensor experiences obstructed view failure when it is blocked because some furniture is placed in front of it, or a magnetic sensor may be obstructed because an appliance with a motor is placed near it. A sensor experiences moved location failure if it is moved to a different location. It may happen if the sensor gets dislodged and someone puts it in a different place. It may also happen if it is mounted on furniture and the furniture is moved to a different place. Okay, but how failure sense is better compared to other solutions? The failure sense detects obstructed view, moved location, and fail-stop failures without redundancy with much less training effort. Detection and classification of electrical appliance activation is not our main focus. Several techniques are available for this purpose that use single point sensing, distributed sensing, or a combination of these two. We prefer to use single point sensing for our work because it doesn't rely on the deployed sensors for which we are trying to assess failure. Let us now see how we are going to approach sensor failure detection. It has two major steps. First step, based on an empirical study, we learn and model the regular behavior of a sensor with respect to electrical appliance activation at home. Second, we monitor sensor behavior continuously and report a failure when we see a significant deviation from the regularity. In the upcoming slides, we will be discussing assumptions, data collection procedure, empirical study to model regular behavior of sensor firing with respect to appliance usage, and how we use this model to detect a sensor failure. We assume that sensors do not fail during the training period. We also assume that sensors and electrical appliances are stationary, that is, they're not moved from their original position in the training period. This assumption does not hold for all the electrical appliances, but as long as it holds for some appliances in each room, like light switches, our solution will work. Extend motion sensors are used in all homes since they are inexpensive. We collect the timestamp and sensor ID of each sensor firing. Several electrical appliances are available in homes, but we use only lights in all homes since almost every room has at least one light and light switches are usually stationary. Since energy disaggregation is not our focus, Z-wave light switches, Z-wave plugs, and extend contact sensors are deployed to figure out when lights are turned on or off. We collect the timestamp and appliance ID of each of the turn on and off events of these all electrical appliances. Deployment and data collection. To learn how motion sensors fire with respect to turn on or off events, of electrical appliances, we use data from two publicly available datasets, houses A and B, and collect data from one real home deployment, which is house C. Houses A and C are four-person homes, whereas house B is a three-person home. The floor plan along with the positions of the motion sensors of house A is shown in figure. The deployment at house C is mainly targeted to detect obstructed view failure. Since we do not have any control over the deployment at houses A and B as they are public sets, and to detect obstructed view failure, we need to obstruct some sensors' view. We deploy a few sensors at house C and obstruct their views. Summary of data collection from three real home deployments are shown in the table. Overall, we use 15 days of data from house A, 35 days of data from house B, and collect 21 days of data from house C. The number of motion sensors, the number of electrical appliances monitored, and the number of turn on and turn off events of the monitored appliances in each house is shown in the table. External motion sensors are used in all homes since they are inexpensive. We collect the timestamp and sensor ID of each sensor firing. Several electrical appliances are available in homes, but we use only lights in all homes since almost every room has at least one light and light switches are usually stationary. Since energy disaggregation is not our focus, Z-wave light switches, Z-wave plugs, and external contact sensors are deployed to figure out when lights are turned on or off. We collect the timestamp and appliance ID of each of the turn on and off events of these all electrical appliances. Let's now discuss about the empirical study and sensor appliance behavior model. Based on the total of 71 days of collected data from the three multi-person homes having 2,818 turn-on and off events of 19 monitored appliances, we tried to understand the sensor firing pattern with respect to the usage of electrical appliances. We now monitor the interval between appliance turn on or off and sensor firing events and observe regularity in intervals for some sensor appliance pairs. As we mentioned before, for most of the electrical appliances, when they're turned on, someone has to be physically present to turn them on. So if there is a motion sensor nearby, it should fire before the turn on event and after the turn on event. If the appliance is turned on the same way all the time, it will take the same amount of time for the sensor to fire before and after the turn on event. However, in reality, people may not access the electrical appliances the same way all the time. Since the movements of the residents are constrained by the floor plan of the house, there are only a few ways to reach to the electrical appliances. If we can collect enough training data, we are able to capture different possible ways the residents can reach the electrical appliances. For some electrical appliances, we should observe the similar behavior for the turn off events too. To characterize this sensor firing pattern with respect to appliance usage, we redefine three parameters, such as IA, IB, and window. Let's talk about IA, which is interval after. Be the smallest interval between a turn on or off event of an appliance and a sensor firing when the sensor firing happens after the turn on or off event. Similarly, IB, interval before. Be the smallest interval between a turn on or off event of an appliance and a sensor firing when the sensor firing happens before the turn on or off event. Note that IA and IB are different for different sensor appliance pairs. We use a window of 5 minutes and don't consider any sensor firing before or after 5 minutes of turn on or off events of the appliances. We keep it fixed for all the homes and in all the experiments. Our subsequent analysis shows that IA and IB are useful features to detect fail-stop failure, obstructed view failure, and move location failure. Now that we characterized the sensor firing pattern with respect to appliance usage, we defined IA/IB. Let's now consider an example from house A. As an example to see how these parameters reveal sensor firing patterns with respect to appliance usage, let's consider some sensors and electrical appliances. from house A. The floor plan and the position of all the motion sensors of house A are shown in figure. We choose the bathroom light and the mudroom light as appliances. We discretize IB values into 3-second bins and plot the distribution graph of IB. The frequency distribution plot of IB sensors with respect to bathroom light and mudroom light are shown in the figure. Note that only the D1 sensor is in the bathroom and other sensors are in different rooms. When looking at figure A, B, and C, if D1 suffers from fail-stop failure, obstructed view failure, or it is moved to some other room, the frequency distribution of D1 with respect to the bathroom light is going to change. IA also shows a similar distribution. The bathroom light clearly helps in detecting the failure of D1 sensor. It may also help in detecting failure of other sensors, example E1. For other sensors, we may need to consider other appliances. Now that we characterize sensor firing patterns or our regular intervals of sensor firing pattern, that is IA interval after and IB interval before, let's now dig into the formula used. Capturing regularity in intervals can be challenging since a sensor appliance pair can have multiple regular intervals. To capture all the regular intervals of a sensor appliance pair based on the empirical study, we use Gaussian mixture model (GMM) to represent the distribution of IA and IB. A GMM has Q components where each component captures one regular interval. The probability density function of GMM is the weighted sum of Q components, which you can see in the equation. Now that we know how a GMM is used in our case, let's take a look at the appliance selection. For each appliance, we compute the probability of each sensor firing within the window of appliance activation events. For each sensor, we choose top K appliances with which the sensor firing is most probable. We associate these appliances with these sensors. It means that the failure detection of the sensors only depends on these appliances. The higher the value of K, the lower are the failure detection latency and precision of failure detection. The value of K can be chosen based on application requirement. We use K equals 2 in the evaluation since the instrumented appliances were limited in our data collection. The failure decision is decided by the state of sensor from the values of PA and PB. If PA less than TA low and PB less than TB low for n times in a row, we report a failure of the associated sensor, where TA delta and TB delta and n are thresholds. If PA less than TA high or PB greater than or equals TB high for m times in a row, we report that the sensor is working fine, where TA high, TB high, and m are thresholds. Also, to avoid flooding of reports, after sending one status report, we suppress all the subsequent reports related to that sensor for the next 6 hours. The performance of failure sense largely depends on selection of the thresholds. Overall, we use 6 thresholds: TA low, TA high, TB low, TB high, N, and M at the time of deciding sensor failure status. These thresholds are specific to sensor appliance behavior, and a static threshold may not work for all possible sensor appliance pairs in all homes. So we compute these thresholds by taking into account specific sensor appliance behavior from the training data. Note that the computation is fairly automatic and it doesn't require any user involvement other than turning on or off appliances while they perform their activities of daily living. The goal is to choose threshold values that maximize precision and recall while minimizing failure detection latency. Coming to the selection of TLO, TBLO, and N, we report a failure of associated sensor if we observe PA less than TA low and PB less than TB low for n times in a row. So as n increases, the latency to detect a failure also increases. As n increases, we report few number of failures, which reduces the recall of detecting a failure, but increases the precision. As TA low or TB low increases, the frequency of reporting a failure increases, which in turn increases the recall, but decreases the latency and precision. Selection of TA high, TB high, and M. We report the associated sensor is working fine when PA greater than or equals TA high or PB greater than TB high for M times in a row. As these three thresholds TA high, TB high, and M are not used in reporting a failure, they don't have any impact on precision and latency of failure detection, but they do have impact on recall. As M increases, we deliver fewer number of reports saying that the sensor is working fine, which increases recall of failure detection. As TA high or TB high increases, sensors pass the thresholds fewer number of times, which again increases recall. The evaluation is based on data collected from 3 real homes. The data collection procedure is described in Data Collection and Deployment section. We use 15 days of data from house A, 35 days of data from house B, and collect 21 days of data from house C. The performance of failure sense is evaluated through a post-factor analysis using these datasets. Instead of deploying the failure sense system in another home, hence the implementation of failure sense is a MATLAB program that analyzes the collected sensor data and reports a sensor failure using the strategies specified in data collection and deployment. It also means that failure sense is agnostic to the purpose of sensor deployment and the applications that are using the sensor data. We evaluate the performance of our algorithm in terms of precision, percentage of failure reports where the sensor is actually failed, and recall, percentage of failed sensor reported. The way we compute these metrics are when failure sense reports a sensor status, we compare with the ground truth state of sensor and determine whether its report is a true positive. TP, that is, we report a failure when it has failed. False positive. FP, that is, we report a failure when it has not failed. True negative. TN, that is, we report a sensor has not failed when it has not failed. Or false negative. FN, that is, we report a sensor has not failed when it has failed. Then we compute precision equals TP divided by TP plus FP, and recall equals TP by TP plus FN. We compare our solution with the state-of-the-art solutions in terms of sensor redundancy, training effort, and scalability in detecting multiple sensor failure at the same time. The experimental setup is different for different types of failure. The precision of detecting fail-stop failure is shown in figure. The average precision is 86.87%. The recall is 100% for all the sensors except sensors F1 and F2, for which it is 0. The average recall is 92.86%. We see that our solution detects failure of all the sensors except F1 and F2 of house A. The reason why the solution fails to detect the failure of sensors F1 and F2 is because F1 and F2 are in the bedroom of house A and the dataset of house A doesn't contain turn on or off events of any electrical appliances in the bedroom. That's why sensors F1 and F2 are not associated with any electrical appliances, and we cannot detect the failures of F1 and F2. Also, the precision is really low for sensor I2 of house B. I2 is deployed in one bedroom of house B, and this is the only room where instead of using light switches, a lamp is instrumented with a Z-wave plug. We are not sure if this is the reason or if this is due to behavior of the residents, but there were no regularity in intervals for I2 with respect to the lamp. That's why although our solution can detect when the sensor fails, it suffers from a low precision. However, we see that the solution performs well for most of the sensors in 3 houses. The precision of detecting obstructed view failure is shown in the figure. The average precision is 82.84%. The recall is 100% for all the sensors except F1, F2, I2, I3, C2, and D1. For sensors F1, F2, I2, and J3, the recall is 0. For sensors C2 and DI, The recalls are 80% and 85.71% respectively. The average recall is 84.49%. We see that we cannot detect the failure of sensors F1, F2, I2 and J3. The reasons for F1, F2 and I2 are as described in the above section. F1 and F2 are deployed in the bedroom of house A and the dataset does not contain any turn on or off events of any electrical appliances of that room. And sensor 12 is deployed in one bedroom of house B and there were no regularity in intervals for 12 with respect to the lamp instrumented with a Z-wave plug in the room. The reason for not being able to detect the failure of sensor J3 is although the view of J3 is obstructed and it cannot see any motion, it used to fire every time a light switch, which is closer to J3, is turned on or off. It may be because the light switch is instrumented with a contact sensor and turning the light switch on or off causes a change in the magnetic field of the contact sensor and causes a small light in front of the contact sensor to blink. We are not sure exactly what caused J3 to fire every time the light switch is turned on or off, but it shows a potential caveat of applying the solution. Appliance selection can be tricky, and if the appliance is close, it may cause disturbances. The precision of detecting mood location failure is shown in figure. The average precision is 90.53%, the recall is 95% or more in all these cases, except in E2 to H1, C2 to C6, H1 to H2, E1 to D1, and I8 to I3, where the results are 91.83%, 85.71%, and 83.71% respectively. The average recall is 89.09%. We select a pair of sensors and move the first one to the position of the second one. Example, in the first case of figure, sensor G1 is moved to H1 location. The positions of sensors along with the floor plan of house A are shown in figure. The dataset doesn't offer us the floor plan of house B. However, from the description, we know that all the sensors of house B in figure are in different rooms. Our solution works well if sensors are moved from one room to other room. However, if a sensor is moved slightly within the same area, it doesn't cause a significant deviation from the distribution of IA and IB, and the solution doesn't perform well. This is why when C2 is moved to C6 and H1 is moved to H2, the recalls are low. Now that small sensor displacement may not make any differences in application semantics, on these cases this type of minor movement is not a movement failure and is not detected as such. Failure sense is generalizable to various types of sensors. For example, light sensor. When a light switch is turned on, the nearby light sensor should see a sudden increase of light intensity within a regular period. If the light sensor is failed or covered or moved to some other room, it will not be able to see that change. We can use this property to decide if the light sensor has failed. Next, the acoustic sensor. When someone turns on TV, radio, washing machine, coffee maker, electric shaver, food processor, hair dryer, or a microwave oven, the nearby acoustic sensor should see an increase of sound intensity or even a sound pattern within a regular period. We can use this property to assess the failure state of the neighboring acoustic sensors. Next comes the water fixture sensor. Sensors that are attached to various water fixtures, example, contact sensor attached to a faucet in the bathroom or kitchen, and sensor attached to a bathroom flush fire within a short time when water starts to flow through the water fixture. We can use this property for assessing the reliability of the water fixture sensors as we detect which water fixture is drawing water by using smart water meter and motion sensor. However, the solution may not be adequate detecting failure of some other types of sensors, example, a temperature, humidity, and radioactivity. But a lot of home healthcare and energy management systems use motion sensors, acoustic sensors, and water fixture sensors to monitor activities of daily living and occupancy patterns of the residents. Such systems will greatly benefit from our solution. To conclude, Failure Sense developed and evaluated a failure detection scheme for sensor network deployments found in smart homes. The solution addresses not only jail stop failures, but importantly, obstructed view and move location failures. New types of failures common in smart homes that are very different to detect even if sensors are made highly reliable and barely addressed to date in the literature or in real deployment. Failure Sense is the first one to detect these failures without requiring sensor redundancy and with minimal training effort. Although Failure Sense has its own limitation, it is applicable to most of the common types of sensors found in real deployments, thereby significantly improving the state of art, and it begins to address complicated and realistic sensor failures with novel insights. Thank